Okay, so let's continue our lectures on the environmental testing. So today I will have a very short recap on the last lecture as usual, because we mainly discussed about the screening, which I think is a really simple thing, so no recap on that. And then we started to discuss about the effects of humidity, and let's have a short recap on that. And then we go to into a concept called classification of environmental conditions. So basically how we can estimate the ambient use conditions. And then finally, let's start discussing about the actual tests themselves. So temperature humidity bias tests, and the if we have the time, then we can discuss shortly about the difference between relative humidity and absolute humidity, which I have already referred a few times. For the literature, just want to point out this Ephraim Suhir's book, which I think is quite good in general for electronics packaging, assembly, and reliability. So it's 2 volumes, relatively large book, and covers quite nicely, let's say, most of the things which we, for example, cover in these lectures. Maybe not the first part of the course that well, but at least the second and the third part. So could be something which you could, for example, if you in your future career will work a little bit more towards reliability engineering, then this might be good book to have in yourself. Okay, and then as I emphasized last time, this book Corrosion and Climatic Effects in Electronics from VTT, that's also extremely nice book for let's say, especially for example, for this part, for the classification of environmental conditions. Okay, so last time we started to discuss about environmental testing, meaning that basically we come back to this our stage gate process, stages 2 and 3. But the point was that now, instead of having only temperature and mechanical stresses, we also include the humidity and impurities. So we can also consider these environmental stresses from the, let's say, these highly accelerated stresses point of view, where the target is more to compare things, find the design mistakes, and so on. And in this stage 2 category, for example, highly accelerated stress test and corrosion test could be included. And now we are kind of approaching the environmental testing in a little bit slightly different viewpoint. So we first look these accelerated life tests, like, let's say, where the stress levels are more reasonable from the use environment point of view, and then we jump from these to the more accelerated tests. And I will also try to explain why this kind of approach has been taken in this course. Okay, so last time maybe the main point, and I really want to emphasize that this is an important thing to understand, that when materials, electronic materials, and especially the organic materials, of course, if we are only thinking about the effect of pure moisture, then basically our ceramics and metals are almost insensitive to pure moisture. Of course, metals are sensitive when you have then some impurities there, and then the corrosion problems start to appear. But if we first think only the effects of moisture, then of course the organic materials, different types of glues, adhesives, organic substrates, and these kind of things, they are sensitive for moisture. And why they are sensitive to moisture is especially because they can absorb water. So basically the structure of all these kind of organic materials is loose. It means that these small water molecules can diffuse and dissolve inside the polymers. And then when you have moisture inside the polymer, then the physical properties, also of course, let's say chemical properties, but especially the physical properties of the polymer is changed. It means that there's quite a lot of space for water to penetrate inside, so absorb these polymers, and we are talking about several weight percentages. And then if this amount of water is inside the polymer, then it changes the properties. And these can be either, let's say, temporary changes, or quite often they are permanent changes, meaning that even if we dry the polymer, it's not kind of recovering back into the original properties. So basically, the main effect is coming from the mechanical strength. One can kind of say that when moisture absorbs, then the materials are losing their mechanical strength. And mechanical strength, of course, also effects on the bond strength, which in turn then means that the coefficient of thermal expansion also increases. And this is already a problem because the organic materials expand as a function of temperature much more than metals and ceramics. This is something that we will discuss in much more detail when we talk about printed wiring board and other substrates. And then also this DG, glass transition temperature, is decreased when moisture is absorbing. So it means that really high moisture content organic materials behave completely differently than dry ones. So with these two pictures, I tried to emphasize the effect of lowering the strength, so either here stiffness or here tensile strength, as well as the lowering of the DG, meaning that the kind of upward drop of mechanical properties. So for example, here this, let's say, high performance substrate material cyanide ester, which as a dry material has glass transition temperature clearly over 200 degrees centigrade, but if 0.5% moisture is absorbed, then the glass transition temperature drops down to 150 degrees centigrade, which is kind of close to the, let's say, standard epoxies. So basically, if you put some money on purchasing relatively or quite much more expensive material, you may lose this advantage, just a small absorption of moisture. Then another important thing was that the moisture intake, or how fast the water molecules are diffusing in the material, and what is the absolute, let's say, solubility of water, is again dependent on the actual structure of the polymer. So how these polymer chains are arranged there. So for example, this was a case example from Suvir's book, that if you have two basically chemically identical materials, so these both underfills are epoxy-based materials, but they have different structure. It means that they absorb moisture at different rate and different extent. So here you can see that this underfill B, it saturates, the moisture content saturates to about 1 weight percent, and it saturates already after 50 hours. On the other hand, this underfill A, after 50 hours, there's already almost 2 weight percent of water, and the amount is still increasing. And it is said here that it was still increasing up to 700 hours. So basically this line continues and continues and continues. And of course, the mechanical properties are basically all the time decreased. So that is the maybe number one thing to remember, that this moisture intake, it affects on the mechanical properties. And also it affects on the glass transition temperature. Maybe I can here now have one case example. This is again years back. It's coming from the telecommunication industry. So this kind of a mechanical part, basically just the box inside which the let's say electronics was put. The company, a small Finnish company, they used a certain polymer material. If I recall correctly, it was polycarbonate, and then for that box. And the size of the box was something like this. What I'm not sure if you can see it from the camera, but few centimeters times, let's say 5 times 10 centimeters or whatever, a little bit larger than a cigarette box. And the electronics was kind of inside there. And then they considered that, okay, this is quite expensive polymer, so maybe we can change it to other one. Now I cannot remember what was it. And then they checked their specifications saying that, okay, the glass transition temperature for that specific polymer was 90 degrees centigrade. And then their customer, the big N, they had, let's say, qualification test procedures stating that all products which they are willing to purchase must withstand this normal 85 for 1,000 hours test. And then these guys from the smaller company checked, okay, the glass transition temperature is 90 degrees, so no problem. This should be okay. It should withstand the 85 test. But then they made the first proto series, put these just plastic boxes inside the 85 chamber, and when they put them in, they were size like cigarette box, and when they came out, they were size like a matchbox and looked like raisins. So they kind of squeezed completely. And then they were coming to us and asking, what does this mean? Because in the specification, it clearly says that glass transition temperature is 90 degrees, and we are testing it only in 85 degrees, so it should withstand. But they didn't consider that the 90 degrees DG is defined in dry conditions. So now when you put it in hot and humid conditions, the moisture penetrates inside and decreases the glass transition temperature, and it decreased more than this 5 degrees. So it went below 85, and then basically the material lost its mechanical strength completely. So this was just a case that if when you look the material specifications, they are always measured under certain conditions. And always when you are talking about organic materials, then you need to pay attention to this effect. So thinking that what the possible moisture intake, how it can affect on the actual bulk properties of the organic materials. And then additionally, we discussed this one, that it's not only the bulk properties of the organic materials, it's also the adhesion, the interfaces between organic and inorganic materials. Like in this case, it's the underfill and then copper laminate. And this shows how the exposure time at different temperature humidity conditions affect the mechanical strength of the adhesion. So how much energy you need to have in order to remove the copper from the surface of the epoxy. And you can clearly see that just bare 85 temperature exposure does not affect practically at all on that. But then when you start adding humidity, then the strength, interfacial strength drops drastically. And the main point here is that this left bar, lighter gray bar, is the moisture saturated value, and then the right little bit darker gray is the recovery value. So basically, even if you drive out the moisture, the interfacial strength has permanently decreased. So it's quite drastic decrease if you drop classification of environmental conditions. So basically, the point is that we cannot measure every possible use environment, especially from the moisture and impurities point of view. Therefore, we need to have some design tools. So again, this is a design aid, which, if you use it properly, should give you the answer for two questions. First, how stressful the use environment is. And therefore, based on that, you can decide that what kind of corrosion or moisture protection is needed, if it's needed. Of course, we hope that the analysis states that, okay, the conditions are so mild that we don't need to do anything. But then, depending on the, let's say, severity category of the environment, then you have different types of, let's say, tools in order to prevent the moisture diffusion or the effects of moisture and impurities. So simple or relatively cost-efficient way is, for example, what is used really frequently in industrial electronics is use conformal coatings. So this is one topic for the second assignment. So conformal coatings are just, for example, lacquer, silicones, polyurethanes, or whatever, which you apply on top of your printed circuit cards. They are not completely hermetic, but they slow down the diffusion of moisture and also impurities. And that's the reason that they will improve the reliability. On the other hand, if the conditions are extremely severe, you may need to use really hermetic sealing, meaning that you need to push the moisture diffusion down to extremely small values. And that could be very costly. You need to use ceramic packages, which can be 10 or even 100 times more costly than organic packaging, and so on. Or you need to use, let's say, for example, air conditioning, heating, in order to, let's say, verify that you are not ending into the saturated conditions, so where the relative humidity could rise up to the 100%. So therefore, we need these kind of tools in order to estimate the, in quotes, average environmental conditions. And this is from IEC, one of the standards which is available. And how then we, let's say, evaluate these conditions? And as I have mentioned already several times, we have two critical parameters, or maybe three. First of course is the temperature and humidity. So these are two. Of course, they are interlinked, as mentioned already several times. And then we have, on the other hand, the impurities. And now let's again start from the pure humidity. And now almost all of these environmental conditions classifications, they are starting the analysis on this kind of a same approach, which is in for example, in this ISO standard, it's called time of wetness, TOW. Time of wetness means, or it's defined here so that the basically that time when the product might see liquid water, so that there are possibility for moisture diffusion and possibly corrosion reactions. And now in this left column, we see 6 different categories from tau 1 to tau 6. And now this is this value is based on the time of wetness. It means that how many hours per year or how many percentages of the use time the conditions are so that the temperature is above zero, because of course below zero we have ice, we don't have liquid water, so that slows down the for example corrosion reactors. And also relative humidity is more than 80%, which means that locally one can have let's say absorption or adsorption of moisture if there's a, let's say, cold spot or something like that. So this is just a way of defining it. So temperature above zero and relative humidity above 80%, and it is considered that, okay, if the conditions are like this, then moisture and intake and corrosion can have an effect on the reliability. And now this is the fraction of the use time, how often these kind of conditions could be met. So for tau1, meaning that we have some kind of a indoor controlled humidity and temperature environment. Maybe one extreme could be like a clean room where you do the microelectronic processing, because there the temperature and humidity are kept extremely constant 24/7, so that the moisture content, for example, can vary only a few percentages. Temperature is kept practically constant within 1 degree. So then we can say that less than 0.1% of the use time one could have these kind of conditions, like when the controlling unit has malfunction or something like that. So I don't think this year we have had, not sure, I think, was it 2 times during the summer when the Micronova clean room, I got the message that the moisture specifications were exceeded because of some equipment problem. So it was a combination of high humidity outside, ambient, and then some equipment problem. And then for several hours during the summer, there was problems with the let's say moisture content in the clean. But clearly it is in this order of magnitude. If we think about, let's say, 10 hours out of 1 year or something like that. And then moving from this tau1 category to, let's say, environments where, let's say, few percent of the lifetime there could be conditions where corrosion could happen. So for example, most probably the space where you are now, where I am now, so normal indoor conditions. Then from few percent up to 10% of the lifetime, then we are talking about indoor storage rooms. Then 10 to 30, for example, outdoor. Some, for example, dry zones, meaning that we are somewhere where typically the humidity level outside is not that high, or in Finland, for example, and so on. Then basically the other types of outdoor environment, and then finally tau6 is something like a tropical zone or greenhouses or something like this, where basically more than 60% of the lifetime these kind of conditions exist. So now we have, let's say, some kind of a rough guess on what kind of time of wetness category our use environment belongs. And now you remember we already have had several of these models, and this is maybe the most commonly known model, which contains both the temperature as well as the humidity part. It's called IRIX model. So we have the Arrhenius part here describing the effect of temperature, and then we have, let's say, similar type of exponential model for the relative humidity. So here we have the relative humidity, and here we have some kind of a constant, and it's this constant you kind of could consider it similar than the activation energy in the Arrhenius model, so that this constant describes how strong is the effect of increasing relative humidity. But this, again, one needs to remember that this is now just for temperature and humidity. It does not include any effects on the other impurities, salt, dust, whatever, which are coming from the environment. And then when we start, I'm going to show you next week some equations where the impurities are also included. And then they become really, really complex, and they might be valid only for certain specific conditions, because they are typically, let's say, analytical equations, which are not really based on any physics of failure, because electrochemistry is way too complex that you could really start from that. In normal use conditions where you have different amount of different types of impurities. Okay, so Eyring's model is the most common one, but of course it is not the only one. And this is just to show, don't even try to remember all these. This is just to show that which kind of models you can find from the literature. So here we have most of the equations have time to failure, TF, and then on the other side you have some constant, relative humidity, and then perhaps some power something or some other constants like this. Here we have water vapor pressure instead of relative humidity and so on. And this is also quite, let's say, typically used, this Sim-Lawson model for acceleration factor. So this is to correlate your use conditions and test conditions. And in this case, this is just a constant which is, let's say, experimentally defined. And if you have different material, then this is also usage change. So maybe I should have put here a constant rather than this number. But it is for one specific material, you can utilize this kind of an acceleration factor between the use conditions and test conditions. After we have discussed about these different types of tests, so most probably, let's say either on Thursday or next Tuesday, I will also show you a little bit more practical examples how you can calculate these time to failures or acceleration factors and compare different types of tests. Okay, so now first, let's say, phase for estimating the effect of the environment was to analyze the amount or probability of moisture having the effect. And then we need to also have some kind of a estimation about the impurities. But now if we think about all possible impurities in the world, of course, we would have hundreds or even thousands of different species. Therefore, this classification of environmental conditions typically concentrate on estimating the most harmful impurities. So those ones which are typical in normal, let's say, use environment, and also those who have, let's say, most of the effects. And therefore, let's say, this is very typical type of way to analyze it. So in this, again, in the left column, we have the, let's say, the pollutants or impurities which are typically in the air and have high effect on the, let's say, for example, on the corrosion reactions for typical metals used in electronics. So we have sulfur dioxide, nitrogen dioxide, hydrogen sulfide, chlorine gas, then ammonium and ammonia ions, chloride ions, and soot. So now these six are very typical. Sometimes only the top four are used. So only these gas forms, not the ions and soot, but either or. Anyway, the point is that based on the average amount of all these six species, the average corrosivity category or air pollutant category is divided into 5 different columns. So P1 is very low amount of on average of these. So here you can see the values in milligrams per square cubic meter. And here if you have, so this is mass per volume, if you have volume per volume, the values are given here. Because of course it's depending how, if you do some measurements, actual measurements, then what your, let's say, equipment will give, if it's giving concentrations or is giving volume for volume percentages. But this is basically not important from now. The idea is the most important thing. So you have categories. The average amount of these most harmful impurities. And then going towards higher concentrations, you go from P1 to P5. Please pay attention to this one. For hydrogen sulfide, we have 2 different values. And this is based on if you have silver in your product, then you use these lower values. If you don't have silver, you can use these higher values. And why is that? It's because we all know that silver is extremely reactive against hydrogen sulfide. So all of you who have even tried to eat boiled egg with a silver spoon know that the reaction is really, let's say, rapid, and the smell which is coming from hydrogen sulfide, it's really ugly. So of course you can try it, but it's not very nice experience trying to eat a boiled egg with a silver spoon. So we know that silver is extremely reactive against this one. So that's the reason to have 2 values here. Okay, so now we have the amount of moisture, and this is, let's say, one, not the only one, but one way of categorizing the most harmful impurities. And then of course you can also, let's say, have measurements. So you can just measure or estimate the effect of your environment onto the, let's say, corrosion resistance of your product. And then when one talks about the, let's say, corrosivity glasses, then quite often these are referred to these ISA G values. So we have here 4 different categories. We have G1, which is corrosivity class mild, moderate, harsh, and severe. And here is an explanation for each category. So basically, if you end up in G1, corrosivity class of the environment, then basically corrosion typically is not a factor which defines your reliability. So basically, it kind of gives you the answer. No, you don't need to think about corrosion. Something else defines your reliability under those conditions. On the other hand, if you end up having GX, the severe conditions, it states that yes, definitely you should do all possible actions to decrease or slow down the corrosion and moisture intake, because only, let's say, products which are specifically designed to withstand these kind of conditions will survive. And these 2 are somewhere in between. And this is just kind of an indicative way of explaining how reactive these conditions are. So it is based on copper reactivity. So how much copper is consumed to reactions in these kind of conditions. So how many nanometers per month copper surface is reacting. Why copper? Because of course it is maybe the most important metal in our electronics. It's quite often exposed, for example, in printed wiring boards. It might have some protective coatings, but anyway, copper is important. And on the other hand, that's also the reason that why copper is used as a reference material in our corrosion tests. So we will see in the next week that how this is kind of utilized in order to control and monitor the actual corrosion testing. So here in G1 condition, the copper reactivity is less than 30 nanometers per month, and in GX it's more than 200 nanometers per month. Okay, these are values which kind of does not tell us much, but of course you could do let's say monitoring. So you could put the pure copper sheets on some kind of an environment, and then after, let's say, 6 months, you take the copper sheets, you cut them, you look from the side, so you make a cross section, you see that, okay, you measure how much copper has reacted during this 6 months time, and then basically you can estimate in which kind of corrosion category you are. Okay, then one case example. This example is also taken from this VTT book. It was this kind of a Nordic corrosion project, so NORCOR project, and what they in fact did was that they actually measured several different typical conditions, general industrial conditions or outdoor conditions in Nordic countries. So basically, if I remember correctly, it was Finland, Sweden, Norway, at least included. I can't remember, was Iceland also involved, Denmark maybe not. But anyway, it does not matter. But we are talking about typical conditions what you can find, let's say, in this kind of a place in the world. So here we have typical outdoor, instrument rooms, fish or meat industry, animal centers, normal industry, horse industry, seashore, car cabin, and greenhouses. And this num here is just a number of those. So basically they had 10 different industrial rooms. They had only one seashore environment and so on. And then they measured over the year, what was the average temperature, what was the average relative humidity, what was the average amount of sulfur dioxide, again, milligrams per cubic meter, nitrogen dioxide, hydrogen sulfide, chloride ions, ammonia ions, or ammonia ions, soot. And based on that, then they defined, based on the relative humidity, they, let's say, picked the time of wetness category, and based on the amount of impurities, they picked the P category, and then combining these two, one ends up with the corrosivity class of the environment. So maybe this is it's not important to go on the details, but maybe we can look at from here. So basically now we have in the y-axis, we have the time of wetness. So the fraction of lifetime where temperature is above 0 and relative humidity is above 80% is increasing to this way. And on the x-axis, we have the average amount of these most harmful impurities. And here they have just marked different types of conditions. So for example, the seashore is clearly GX, extremely severe condition where you have both high humidity as well as high amount of impurities. And for example, greenhouses, the humidity effects are high, but typically there is quite low amount of impurities. Therefore, the greenhouses belong to this moderate corrosivity category. So these dashed lines here, they kind of separate the different corrosion categories. So G1 mild, which basically don't need any protective actions. G2 X here, which you definitely need, and then G2 and G3 are here in the middle, and then it depends on your reliability targets, your materials, and so on, what kind of corrosion protection or moisture protection you need, if you need it. Okay, so this kind of concludes the classification of environmental conditions. Hopefully you got the point. So because direct measurement is not possible for all environments, then you should have some kind of a model environments where you can, let's say, predict the average conditions, and based on these average conditions from moisture viewpoint as well as impurity viewpoint, you can predict how severe these conditions would be for an electronic product. And based on that, you can decide if some corrosion protection or moisture protection is needed or not, and if yes, then what kind of corrosion protection you could do in order to verify the reliability. Okay, so basically now we have gone through the let's say the principles, the effects of let's say moisture, and then also how to estimate the use environment. And now let's jump to the testing part. So this might be, at least in the beginning, a little bit boring, as I will be just explaining one typical testing standard as an example. But let's go through these, and then later on we can have, let's say, more case examples how these kind of tests are utilized, how you let's say you can have these acceleration factors, how you can estimate the lifetimes, and so on. So anyway, the accelerated environmental testing, typically it's meant that you have high temperature, high humidity, and then possibly some kind of an electrical bias. So it could be, let's say, just a few volts, normal operation. These are more common ones, but then also it could be, let's say, high voltage tests. And I think I forgot to say in the beginning that I agreed with Jonas, the guy from ABB, that he will also participate next Tuesday lecture in the morning and give a short, let's say, presentation, if he has the time, also what kind of, let's say, high temperature, high humidity, high voltage test they are doing for the IGBT module. So the video which he presented, or was included in the previous lecture, that was on combined loading, temperature cycling, power cycling, and now for basically for similar type of products, how the environmental, let's say, impacts are estimated or tested. So let's see what he can deliver for next week. Or yeah, if he doesn't have the time, then I will have a short, let's say, a few slides on that. Anyway, the point is that we combine temperature, humidity, and then possibly some electrical stresses. And one thing which maybe it's good to mention already in the beginning is that when we are talking about tests which contain humidity, then almost always these tests are destructive. What does it mean in practice? If you think about our last lecture and the objectives and tools for screening, and we had one requirement that, okay, if we use tests for screening purposes, then we shouldn't affect those good products which we want to allow to go to the market too much. And as humidity tests are destructive, it means that typically you don't use, there are exceptions, but typically you don't use temperature humidity tests as screening tests, because you don't want to, let's say, force moisture inside your product. As we saw, it might not be recoverable change, it could be permanent change. So you are cutting off significant, let's say, amount of lifetime, or you are decreasing the mechanical strength of the product permanently with that exposure. So that's the reason that hot and humid conditions are typically excluded from the screen. I think this is good to keep in mind. And on the other hand, if one thinks about the most commonly used reliability tests during the last 50 years, 60 years, they are either thermal cycling or temperature and humidity. So there's huge amount of different types of combinations of temperature humidity tests developed during the last decades. And therefore, in order to have some kind of way to compare results, then we always need standardized tests. So there's a clear need for standardization, and that has been done during the years. And now let's say, outcome from that is that we have huge number of standards. So also now the amount of standards starts to be so high that it's not that straightforward to, let's say, make your decision according to which standard we should do our testing. Of course, it can be, let's say, again, this field of industry dependent, or it can be an agreement between the manufacturer and the customer that what kind of standards are used, or then you just need to pick it yourself. And here is just a table showing different types of humidity, temperature, humidity related standards. So no impurities here. All these standards are, let's say, only concentrating on temperature and humidity, just with different parameters. So here you have the different names. So there's Japanese standards, IEC standards. There are there any MIL IPC standards? Are there any MIL standards? No, not in this, but basically there could be also some MIL standards also here. So, okay, because this is let's say, excluding those extremely severe conditions like liquid to liquid dipping, which is a kind of a combination of different, also includes the thermal shock effects. But anyway, so I have tried to, let's say, color code the important things in this table, because there's basically 4 or 5 different types of temperature humidity tests. Most common are these which are marked with the blue color. So this is what in a minute I'm presenting you, let's say, not all every word, but quite in detail what this IEC 68-2-67 contains. So because that's the, let's say, classical 85 standard, which is one of the most commonly used standards in the world. So it's so-called steady state temperature humidity tests. So we are staying below 100 degrees centigrade. We have constant temperature and humidity exposure. Then we have these, let's say, marked with red, and also basically this turquoise, is that correct name for this color, where we are still staying below 100 degrees centigrade, but we are cycling something. And as we already know, relative humidity and temperature go hand in hand, so we cannot just cycle one. If we change one, the other is also changing. So basically, we are cycling both the temperature and relative humidity. And the objective is to cause purposely this new condensation. I will come back to this in a minute. And then we have these 2 other types of tests, the green ones and the purple ones, which the point is that we need higher acceleration, and therefore we go above 100 degrees centigrade. Because we cannot go over 100% for obvious reasons. We can go over 100 degrees centigrade, but also we all know that water is boiling at normal pressure in 100 degrees centigrade. So it means that we need to increase simultaneously the pressure in order not to avoid the boiling. And therefore we have these unsaturated, pressurized tests, which are under a name of HAST, highly accelerated stress test. So this is what I had in the first slide, referring that the point is kind of identical that what we have in the HALT testing. And then we have, let's say, the older highly accelerated tests, which are called also pressure cooker tests, which are saturated conditions. So basically there we have pressure cooker, so we have liquid water, and then we have extra pressure to allow the increase of temperature. And then either today or then on Thursday, we discuss a little bit about the difference between these kind of unsaturated and saturated conditions, why one should use either or. But okay, let's start from this one now. So steady state temperature humidity tests. So as I said, this is a test where basically this kind of test has been existing at least for 50 years already. So the point is that typically you have quite high temperature and high humidity, and then you either have constant power on or you have cyclic power on, depending also a little bit about how much power losses your product is generating. Because again, if you have, let's say, high power losses, it means that locally the temperature is increased. What that means is that locally the relative humidity is decreased, even the absolute humidity stays the same. And then that might cause that you are not seeing the real effects if you have continuous power on. I will come back also this issue in the final case example of this, let's say, second part, when we discuss about corrosion testing and the same effect that you also should think that if you add some power, then what it affects on these kind of reactions, because then you might locally kind of dry off the ambient. So it may not be that always when you put some additional stress, then you have an, let's say, cumulative effect. You could, let's say, speed up the failures. Sometimes it can go on the opposite way. Okay, but anyway, the point is that you have a certain parameter, typically is a resistance, which you monitor, and then during the exposure, and based on that, you try to estimate the effect of this kind of a hot and humid condition on the reliability. Here is just showing which kind of chambers typically one have. So again, this is not an advertisement of any company. This is just let's say our previous hot and humid chamber. So coming from Weiss, the German manufacturer. So these have been really good and robust chambers. But basically, it's a kind of a quite large. So if we think about the dimensions, this may be 1.5 meters, 1.5 meters, and it's a little bit more than 2 meters high. So they are clearly larger than, for example, your normal refrigerator. Of course, quite much dependent on the testing volume. So here the testing volume was, well, if I remember correctly, I would say a little bit more than 0.5 meter in every dimension. So not 1 meter, but maybe, let's say, 70 centimeters on average dimension. So you can put quite large pieces inside. As you need temperature and humidity control and also thermal control, then of course you need this lower part is typically having the compressor unit for the cooling, and then also making the humidity from the water. And quite often, as also this one, is that you have basically a possibility to use these chambers also for thermal cycling. So basically, you can either have pure thermal cycling without humidity, and these are the, let's say, temperature range, and this is, I would say, quite nice range. Typically, the lower temperature is less, close to minus 50 degrees centigrade, and I'm not even sure if our equipment never went to these cold temperatures. And then relative humidity between plus 10 to 95% relative humidity. So of course, it's the purpose of this course is not to go into very details in the, let's say, equipment themselves, but just want to show you the basic principle of how you, let's say, make this kind of conditions. So basically, you have here, by the way, SSR means solid state relay, just controlling unit. So here you have, let's say, water, which you heat. So you, let's say, produce a moist fume. And then you have your dehumidifier, cooler, and heater, which you can control. You have the fan, and here you have the temperature and humidity measurement. So basically, you boil water, make the water steam, and then based on your measurement from the working space, you either heat it up, cool it down, or try to get rid of the humidity, and you have a fan so that you have, let's say, as equal conditions as possible in the working space. So this is just a, let's say, simplified way of considering how temperature and relative humidity can be controlled. One important thing which I also want to mention is that you should, let's say, make sure that when you are doing the testing, the surfaces of your test equipment, device under test, can be exposed to the testing ambient. You shouldn't block the airflow. So this is good arrangement. This is not because there's too small space between the samples. So quite often, instead of placing the samples side by side on a tray or something like that, you try to, for example, hang the samples so that the airflow would be as uniform as possible. And then also you need to be sure that you don't have any effects on coming from the actual equipment itself. So for example, we all know that if you let's say remove your refrigerator when it's let's say on and you touch the compressor, it is extremely hot. So also you want to make sure that the equipment, running of the equipment does not, for example, create any hotspots. Therefore, there are, for example, here in the standard, it is defined that what is the actual volume where you can put your sample with respect to the real test volume. So basically these light lines here, they are referring to the inner volume of the test chamber. And this grayish cube here is the volume where you should put your samples. So you cannot put them too close to the walls or roof or bottom. So basically here, the minimum spacing is either 5 centimeters or 15 centimeters based on the total volume of the, let's say, the chamber. So these kind of, let's say, additional requirements might be coming from the test standards in order to make sure that if you put 50 samples simultaneously inside the chamber, so they will all see same and the correct conditions, and not that the ones who are in the corner is seeing, let's say, higher temperature than those which are in the center, or vice versa, or high humidity, because that of course increases the scatter of your widens the distribution. And when distribution is wide, then also always your conclusions are more difficult to make. You need to have the statistical mathematics in order to really see that what is there a difference or not. And therefore you would like to have narrow distributions. And this is one way to verify that. Okay, so as I said, I will have an example on how these, let's say, standards look like, because of course with the copyright policies, I cannot kind of give you, just put in my courses this actual standard, because that is something that even I am part of IEC and this committee which makes these standards, I cannot get them for free. So basically you always need to purchase the standards. So therefore I have kind of taken from the standard all the relevant data and have it in this kind of slides way. It is a little bit boring, but maybe it's also helpful for you to see that if you have not been involved with the standards yet, so you see that what these standards define and what they leave open. And this is also quite much question of what kind of a, let's say, standard field you are in. So as these IEC standard, they try to be generic, global standards for all possible electronic equipment. They are, let's say, the requirements are a little bit more loose. They are maybe more ways that how you should do the testing, and then you need to report if you, let's say, deviate from the actual recipe. But it is not, there are a little bit of freedom. There are some things which are, let's say, compulsory, so you will see that you shouldn't do something, but then there is a little bit of flexibility within. On the other hand, if we think about these, let's say, qualification standards that some industrial fields have, then they are clearly go, no go. So you need to show that, okay, your product is does pass this test. Then there's no, let's say, everything is specified. You need to do it like this. If you do something else, it's not accepted. Even if you have a power cut during the test, if the standard test standard states that, okay, you cannot interrupt the test. If there's a power cut in the whole area, whole autonomy will be black, all testing chambers will go down. If you have this kind of a standard, then you need to start it from the beginning because it's not accepted. Okay, so as I said, this is the, let's say, if not the most commonly used reliability test in the world, at least the second most common. So maybe this IEC 68 series for thermal cycling could be even more commonly used in electronics in the world. Generally, but if this is definitely the second one. So it's very, very, very commonly used standard. So also it is used for several other purposes where it's not supposed to be used. So actually the standard says that this test is meant for evaluating the changes in resistance in non-hermetic packages under hot and humid environments. So meaning that you should use it for non-hermetic components like overmolded packages, PGAs, QFPs, whatever, and the effect should be changed in the resistance, not, for example, a corrosion. Even really often we see that corrosion plays a major role in the failure. But then if the test is run correctly, then the corrosivity comes from the product itself. So the impurities are coming from the product. It's not coming from the test environment. But still, that kind of shouldn't be accepted. So the idea is that you have a high temperature high moisture content and the water vapor has a higher pressure in the test ambient than in your product. So there's a driving force for diffusion of moisture inside the product, and that would change the resistance, which you can somehow monitor, and that would be your failure criteria. So this is another thing which now gives freedom in this standard. It only states that samples are typically biased, meaning that it can be biased or it can be without a bias, and it is not stating that what kind of bias you should use. So is it normal 5 volts operating voltage or something else? So it's dependent on your product, if you want to use it or not. Okay, then there are, in the standard, there are requirements for the equipment. First of all, it needs to be operational minimum of 2000 hours. So it means that you should be able to run it without any interruption. So for example, you consume humidity, water there, so you need to be able to add water without ramping down the process. And minimum of 2000 hours, so a little bit more than 2 months. Why is this 2000? It's coming in within the next few slides because we have one category of test which takes 2000 hours. Then the system must be able to measure, but not only measure, also control the temperature and humidity in the whole test chamber, and also during the test ramp up and ramp down. So basically you need to monitor when the temperature and humidity is ramped up and ramped down. The moisture which you use must be continuously removed. So you cannot recycle the water, because if some impurities are dissolving from your product, then the amount of these impurities would accumulate during the test, and then you would start seeing these, let's say, electrochemical effects. Therefore, you need to always have fresh, pure moisture exposure to your test devices. And important thing, condensation is definitely not allowed. So in every location, the relative humidity must stay below 100%. So again, no significant corrosion, and these samples may not release any chemicals which would change the chemical composition. Also, of course, the chamber should not release anything. So that's the reason that these kind of chambers are always stainless steel chambers. So nothing is dissolving from the walls of the chamber, which could also change the testing ambient. Here are some additional requirements for the equipment. So the temperature tolerance is ±2 degrees for the whole testing volume. The humidity tolerance is ±5%. Then there's this little bit vacuum expression, no significant air circulation inside the chamber. So that is, let's say, quite a difficult thing to really quantify. But what this means is that you cannot, let's say, achieve this, for example, the evenness of the temperature just by putting there a huge fan where you would have really a turbulent flow inside. You should have nice controlled flow of air, but not too high. And this is, of course, sometimes quite difficult in the standards if you don't have any, let's say, quantitative number or anything like that describing the, let's say, the parameter. But it is like that. Then for the water itself, which is used to make the humidity. So of course, normal tap water is not, you cannot use. So it should be either distilled water or deionized water. And here are a few requirements. So the pH must be between 6.0 to 7.3. at the temperature of 23 degrees centigrade, and then the resistivity of the water must be at least 0.5 megaohm centimeter at this temperature. Meaning that, of course, this is coming from the impurity, amount of impurities in the water. That's the reason that one uses distilled or deionized water. And of course, always before you start the system, then you need to clean the walls and everything so that no residues from the previous test is there, which could, let's say, affect on these purity values. Then the severity of the test. So in this standard, the severity is, let's say, defined so that you have different duration of the test. So there are 4 different classes. The first is 7 days, class 1, and the class 4 is 2000 hours, so 82 days or whatever is that. Maybe the most common is this class 3, is 1000 hours, 85. So it's 41 days. That's maybe the most commonly used test. So some standards, of course, you could have that the severity is based on the actual stress parameter, so that you could have a class 1, which the relative humidity would be 60%, and then class 4, where the relative humidity could be 95%. But here, the severity is just the duration of the test. So then, before the test, you should have the normal, let's say, testing, visual, dimensional, functional test. You need to record how your system is working, what are the dimensions, and so on. Maybe take a few photos, how it looks like, and then you start the actual process. So here is the testing process itself. You need to be sure that the samples are not subjected to heat during the test equipment. This is especially true when you ramp it up, because while heating, then of course you need more heating power than keeping the temperature constant. So this could be a challenge. So you cannot exceed the tolerances, for example, the temperature tolerance during ramp up or ramp down, meaning that quite often you need to heat it up, not with the maximum speed, but with the controlled speed, because of course, quite often, if this is your target temperature, when you start heating it up, then what you end up is something like this. So you need to be sure that this is plus minus 2 degrees centigrade, because that was the our temperature tolerance. So this is especially important part here. Okay. And then important thing is that if you use biasing, so you put the voltage on, power on, then you should not put it on when you start the test, but when the target conditions you have reached. So when the temperature is 85 and relative humidity is 85, plus minus 2, plus minus 5. On the other hand, when you do the ramp down, then you keep the bias during ramp down, which is maybe a little bit unlogical, but this is how it has been defined. You must have this ramping up done in less than 3 hours, and you start counting the test time when you have reached the conditions if you put the bias on. So the test time, this ramp up time, is excluded from the total test time. And then after the test, you should return to the normal temperature pressure conditions within 1, but not more than 4 hours. So you also need to kind of slowly ramp down the process, testing process. Okay, there's a question. vacuum chamber. So of course the problem with the vacuum would be that you decrease the boiling point of water by putting it into vacuum, and so basically you dry out the sample. That is quite often. I used it yesterday, the same purpose, to dry out some of my samples. So I did some grinding and polishing. My sample was a resistor, power resistor was porous, and I know that water went in the structure. Then I put that one into the vacuum in order to remove the moisture, because I cannot put moisture in my scanning electron microscope, because there it's very high vacuum inside. So in that sense, I don't see the sense for using, let's say, vacuum together with moisture, but you can use vacuum, of course, to dry out your sample. Now I'm not sure if I understood your question correctly, but that is basically the point. Okay, good. Then measurements. So this is now the critical, let's say, or I think it is quite critical requirement, is that if you do some measurements, which you should do, so you should monitor your samples, you should do it in situ, meaning that you should have some wires through the walls of the test chamber, so you can do in situ monitoring. So it is not allowed that you keep the samples, for example, there 250 hours, then you remove them, do the electrical testing and put them back. So according to this standard, this is not allowed, but this is what people do very commonly do. Because if you have even a little bit complex test device, so a real board, it's really, really difficult to have the in situ monitoring. So you would maybe prefer to have the testing done in a test rack or something like that. And then, of course, removing it. But in principle, this is not allowed. The minimum thing is that you at least need to put it in the report that, okay, this was done, and agree that one, whomever you are kind of targeting this test. If you're doing your own product development, of course, then you are free to do whatever you want. But if you claim to your customer that this product has been tested according to this IEC 68-2-67 standard, then you cannot do it if you have interrupted the test, because when you interrupt the test, you remove the samples, then the moisture which has penetrated starts to dry out, and that maybe. Sometimes also there's a practical reason for doing the testing, so that you even dry it out and then do the test, because if the product is, let's say, too moist, then you do some electrical testing, you can have some electrical breakage of the system. Okay, and then after the test, you leave the samples minimum of 2 hours and maximum of 24 hours, and then you do the same measurements what you did before the test. So you take some photos, you make the dimensions, measure the dimensions, you make the functional measurements, and so on, and then you report everything. So then the results you are reporting like this. So test duration, test conditions, the samples before the test, and all the measurements, and so on and so on. No, quite let's say, straightforward what you need to put into the results. But okay, hopefully, I know that this was a little bit boring to go through a standard, but hopefully it was also, let's say, helpful for you to understand what kind of, let's say, instructions and requirements these standards give. And once more, want to emphasize that, of course, depending on the type of standard, then there might be more this kind of compulsory things, or things which are completely forbidden, or they can be, let's say, more like a direction how you should do it, but you have more freedom within the standard, as long as you then include all those details into the reporting so that the, let's say, the customer knows what you really have done. Okay, so now we have a few more minutes time, so let's quickly check the let's say, other types of temperature humidity tests, especially these cyclic ones. So here is a same, let's say, standardization glass. So again, IEC 68 and now 30, number 2-30 standard, which is the cyclic temperature humidity test, which the point is that first you heat the system up and you increase the relative humidity, let's say, close to the 100%, but not to the 100%. And you have high absolute humidity there. And then when you start cooling down, then basically during the ramp down, then the relative humidity increases to 100%. So basically at this stage, you start to see dew formation or condensation. So the surface of your, or part of the surface of your product will be covered with the film of liquid water. So that is the point. And then you can have different versions. So here, this the temperature is a little bit higher, and then has 2 cycles where the minimum temperature is room temperature, and then the 3rd cycle is that you go to -10. So the obvious, let's say, purpose for this is that first you get the condensation, and then you get the ice formation, and that is could be mechanically really, let's say, rough test, so that if moisture goes inside the product and then you form ice, we all know that the volume of ice is much larger than the volume of water, liquid water. So basically the ice expands inside the product and can cause then mechanical stresses, cracks, delaminations, and these kind of things. And here I have a, let's say, a standard which is so-called new proposal NP. So it is still under construction, but this is another type of cyclic test. So here you have, let's say, different phases in the cycle. So basically, this is one cycle here. And here in this table, you have different test conditions, 1, 2, and 3, which defines that what are the, let's say, the conditions in different zones here. So you have different times, different time temperature, temperature humidity, let's say, conditions, and going from lower temperature to higher temperature, and so on. So different types. So this is just again another example. So now we have, let's say, covered those temperature humidity tests where we stay below the boiling point of water. So next we would start discussing about these, let's say, pressurized tests where we can increase the temperature, like here and here above 100 degrees, and then either being below the 100% relative humidity, so unsaturated testing, or above. So we have 5 more minutes, so I will start few simple slides on really pointing out what is the difference between relative humidity and absolute humidity. And if we look at it from the, let's say, fundamental chemistry point of view, those of who have read a little bit more about physical chemistry, you may know this Clausius-Clapeyron equation, and this is basically the equation where you can calculate the absolute air humidity if you know the relative air humidity and temperature. But this is, of course, not important. This is just how you calculate what is the fraction of saturation, so the relative humidity, and what is the absolute amount of water, so how many grams of water per cubic meter. So in the textbooks, you have these kind of tables or figures. They are quite often called either climatograms or Molière diagrams. So this is taken from the PTT book. So basically here you can see an example. So if you have a temperature of 14 degrees centigrade and the relative humidity is 80%, then by following this curve, you see that we have the absolute humidity is about 10 grams per cubic meter, and the saturation temperature you can read from this point. So basically, what is the temperature where 100% relative humidity is met with this absolute humidity, and that is something like maybe 12%. Let's see if we can end up our lecture with this, my fancy Excel. Does it work? Yeah, we need to, just a second, click of the laser pointer. Let's see if this opens the Excel and if you can see it. Okay, do you see the Excel now, or do you still see the slides?
It's still the slides.
Sorry? You see the Excel?
No, the slides.
Okay, then maybe I need to stop share. Share screen. Maybe I'll share just the screen. Hopefully you now see the Excel.
Yes.
Good. And now I think I just realized that I'm hearing your voice from the laptop, not from my headphones. So I hope that my voice has been clear enough during the lecture. But as long as nobody commented, I hope that you have heard what I have said. Anyway, so this is just an Excel which I made based on this previous equation. So if we now put the same example here, so 80% relative humidity and 14 degrees centigrade, then we see that the absolute humidity is 12 grams per cubic meter, and we see the saturation temperature. So if we start increasing the temperature, let's put the sauna conditions, so 80 and 80, then the absolute humidity is increased drastically. So going to several hundreds of grams of water per cubic meter. So of course this means that when temperature is increased, then you in absolute values you have more water in the air. So then also the driving force for diffusion is increased. And also this meaning that if we go back to the, let's say, 4 degrees and 80%, we see that the saturation temperature is, or maybe put here 95 or 95. So you have only 0.8 degrees where the saturation temperature is. So that means that, for example, in the morning, when it's cold night, your internal part of your car is colder than in the morning when the external temperature starts to heat up. It means that your windscreen is colder than the air. So the moisture which is in the air is saturating in your windscreen, and you have there water drops, which is of course problem of seeing anything when you start driving your car before it, let's say that it heats up the internal compartment. Okay, so now I think again time is up, so I will stop sharing